In many applications, such as neural networks, we encounter multivariable functions quite a bit. And there's a process called gradient descent that is used to actually optimize those functions. But first, it is important that we learn a little bit about multivariable functions and their rates of change. So any function that has exactly one output, that's the key here, but has multiple inputs is called a multivariable function or a multivariate function. And what we should notice right off the bat here in this notation is we have kind of the standard output notation like we would say in regular algebra, univariate algebra. That means one variable algebra. We would say y is equal to f of x. And then we'd maybe have some expression for that, say 2x plus 3. And this is often called the name of the function, and we could represent it either way as either z or f of xy, just like we could call the output y or f of x. Now, the advantage of the function notation, of course, is that it allows you to specify what the inputs are. Notice that there are two inputs here, x and y, and you have one output, z. And both of these guys, x and y, I'll just draw this little diagram, are used to determine the value of z. In this case, the way you calculate z based on x and y is you take the negative of x squared minus y squared and add 3 to it, and you get your output. So for example, if we were to calculate what is f of 0 comma 0, well, that would be for an x value of 0 and a y value of 0, we'd get negative 0 squared minus 0 squared plus 3, which gives us an output of 3. So what does that mean? Well, here's actually this surface. This is what we call a paraboloid. Notice, looks like a quadratic function in both variables. And here we have an x-axis and a y-axis. But we need a third axis because we have 3 variables, 2 inputs and 1 output. So we have what we sort of can refer to here as the input plane. Okay, a plane is a flat surface, and it's an input plane because every single ordered pair represents an input. And then to represent the corresponding output, we'd actually need a third component. So that represents this point right here at the top. That is an x value of 0. So along this axis, we would go 0 units. Imagine you're standing at the corner of a room, and you go 0 units in one direction, 0 units in the other direction, but then 3 units in the z direction. So this ordered, we can't call it a pair anymore, it's an ordered triple, would be the point 0, 0, 3. Or you could represent that as, or to say f of 0, comma 0 equals 3. And at this point, of course, we notice one thing, that is the maximum of it, and that's what we would be interested in locating using the concept of rates of change. So we actually have not just one rate of change, we have 2 rates of change. How does our output respond when we change x versus how does our output respond if we change y? So for instance, maybe z represents a crop yield, and x represents how much water you give your crop, and then y represents maybe how much fertilizer. So we may want to know how much does your crop yield change if you increase the amount of water by 1 unit versus how much does the crop yield change by when you increase the amount of fertilizer by 1 unit. And so we have names for these. We could say instead of dy dx, we'd actually say dz dx. So that would be the change in z divided by the change in x. Now notice that we're using this partial notation here, this partial operator. That is the same thing as saying, dz dx, but in multivariable calculus, to indicate that there would be more than one input, this notation is often used instead. It means the same thing as saying dz dx, but we will use the partial derivative operator. And so that's asking, if we change x, how does z change? And if we change y, how much does z change by? Okay, so again, if we think in terms of crop yield, how much does your crop yield change by if you increase the amount of water you give it? How much does your crop yield change by if you change the amount of fertilizer you give it? Unfortunately, we can't call this z prime anymore like we would in regular univariate calculus. So back when we're looking at this function, we might say, well, y prime, its derivative would be 2. It would be the slope of that function. This is a line, so the slope of 2x plus 3 is just 2. But it would get a little confusing if we just said z prime, because we really wouldn't know whether that's a change in z because of x or a change in z because of y. And so rather than to use the prime notation, dz dx can actually be written in terms of the function notation as f sub x of xy. So this is dz dx. That's the function that would say, well, what happens to z if you change x by a little bit? And this would be the same thing as saying, how does z change if you change y a little bit? And it's more convenient to use this notation because, of course, you can specify what inputs you're feeding it. So keep in mind that the point will rely on 2 values, but then how much is z changing by at that point? And similarly here, if you look at a specific ordered pair on the input plane, how much will z change by if you change y by a little bit? So dz dx tells us how much z is expected to change by when x increases by 1. Okay, so usually we say increase by 1, but we know that derivatives is just all tiny, tiny changes. But in theory, that number would say, here's how much z should change by if you change x by 1. Then dz dy tells us how much z is expected to change by when y increases by 1. So we won't go over computing the derivatives in this video, but I'll give you one example of our multivariable function. At the point 0, 0, okay, where we were up here, at this point 0, 0, when x and y are both 0, z is equal to 3, how much does z change by if you increase x by just 1 unit? Well, it actually increases by 0 units. And similarly, if you change y by 1, at the point 0, 0, how much does z change by? Well, it changes by 0 units. So what we're saying here is if you were standing at the top of this paraboloid and you were to move 1 unit in the x direction, then you would at that instant expect z to change by 0. Okay, similarly, if you change y by 1 unit, okay, this is again, in theory, this is just instantaneous. At that instant, how much would z change by? Well, it would also change by 0. Okay, well, that is actually powerful information because we know that at this peak, we have a maximum. And typically at maximum, a rate of change is equal to 0. So if I thought in terms of 2 dimensions, and I looked at this point right here, and that's a maximum, we know that this is y and this is x, we know that f prime at that point, we'll just say this is the point, maybe this is an x value of 2, f prime of 2 would equal 0. But when you're dealing in 3 dimensions, there's actually 2 primary directions of change, the x and the y, and what would be analogous to the slope of the tangent line in 3 dimensions would be the slopes, plural, of the tangent plane. So imagine that what we have here is actually these slopes indicate the 2 tilts that would be associated with a plane, a sheet of paper. Now imagine a sheet of paper, right? You could take a sheet of paper and imagine this is a 2-dimensional sheet of paper. You could tilt it this way or this way, right? From this end. So you can make the sheet of paper look like this. But you could also tilt it, along the length, right? Along this way, you could actually tilt it back and forth to maybe make it look more like this, right? I could kind of tilt this thing. I don't know how you describe it, maybe a rotation in either direction, this way or this way. And then you could also lift the ends up and down, so you have two different points of rotation. Now in our case, because the slope in both directions is 0, what you would imagine is this to be a flat sheet of paper sitting on top. Now, the idea is if you take a two-dimensional function and you zoom in on that point, what you should see is a straight line, if you zoom in enough, with a slope of 0. I'm going to show you. Now, if we zoom in on this point in 3 dimensions, what we should see is a flat sheet of paper sitting perfectly horizontal to the surface, the xy input surface below. So here I just have negative x squared plus 3, and this is kind of similar, right? Because we're looking at a 3-dimensional graph that has negative x squared minus y squared plus 3, but in a 2-dimensional function it would look like this. And the idea of the slope of the tangent line at the point x equals 0, the slope of that tangent line would be 0. And what I should see when I zoom in close enough is that I get local linearity. I basically approximate that function as I zoom in enough. Notice that that's a horizontal line that has a slope of 0. Now if I look in 3 dimensions, you can rotate this all around. You can see it from the bottom. It kind of looks almost like the tip of a bullet, or perhaps a funnel of some sort, almost conical in a way. When I zoom in on the top point here, watch what happens. Okay, you can see it's still dome-shaped, right? But as I'm zooming in more and more on that point, what we should see is that the slope of that surface gets closer and closer and closer to being a surface that is perfectly horizontal to the XY input plane. Okay, try to zoom in as much as I can here. Maybe it takes a little bit more effort to do that here, but you can see that that plane is nearly perfectly flat. And that is precisely what we mean by the slopes in both directions being equal to 0. That fact happening could actually be one of a few possibilities. It's not necessarily just a min or a max where you get these critical points. You could actually have what's also called a saddle point, and we'll explore that a little bit more later. And so here's what we can do if we want to locate critical points. We can take the derivative with respect to x of our function, the derivative with respect to y of our function, set each of them equal to 0, and then solve that system of equations for the x and y where there is a slope of 0 in both directions. We'll learn how to do that soon.